Okay. I need to change the name of the stream. This might interrupt the stream, but whatever. Sucks. Okay. You guys hear me all right? Okay. We're ready to start. There's a little delay here, but it's going to help me out. Let's see. It's dropping frames left and right. That's cool. I wonder if I can mess with the bit rate. Is it not showing? I think kind of looks green. Yeah, well, whatever. Okay, so we're just gonna start and start at the beginning with, here we go, nondegenerate perturbation theory. So the basic equation, you do, this is the basic Schrodinger equation, and then we'll put the ends down here, or time independent Schrodinger equation. Don't bug you with this. Okay. We take the time independent Schrodinger equation and we break up the Hamiltonian and the energy levels and the wave functions. All of those get broken up into individual components. One that's amazing, that's much larger than the other one, and then it's kind of a perturbation. It just adds a little bit to it. So what I'm going to do is I'm going to note these all with zeros, and that's the 0th order perturbation, i.e. no perturbation at all. And we're also going to bring this in, this fact here. I can do a much better psi. It should be m and n, micro delta. So basically all the wave functions are orthonormal. You take the inner product of it with itself, then it becomes 1. If you if there are 2 different ones, then it's 0. Nothing too new there. Moving on. What we're going to do is we're going to do a slight modification. What we'll want is we're going to do kind of expand these out. This becomes 0 plus h prime. Right, so this is the original one, this is the perturbation. We want, well, what we'll eventually want is this. Right, where these ends are the perturbed wave functions, this is the perturbed Hamiltonian, and this is the energy. So the n is pretty simply the sum of all the En m's. Likewise, psi n is the sum all the m's of psi n. Okay, so those are just definitions that we're going to bring in. So now this is all in Griffiths. There's nothing new here, but I don't like the way the Griffiths does it, because what he does is he takes this and says, okay, we're gonna rewrite it as h0 plus lambda h prime. We're gonna rewrite this as times lambda to the m and times lambda to the n. But here's the thing, all of the lambdas are 1. So this doesn't do anything, it doesn't add anything in there, but it's kind of there to keep track of everything. So I'm not gonna do that. Instead, what I'm gonna do is I'm gonna introduce some kind of new things that are kind of normalized so everything's approximately the same size. So what I'm going to do is introduce this concept lambda, where we take this guy and we make it equal, approximately equal lambda. Now, there's no, it could vary from term to term. I don't really care too much, but it's going to be around the same value when you actually look into what they kind of are in general, or you can make it around the same value. It's not too much of a big deal. So I'm going to introduce this lambda, and this lambda is going to mean something. It's not going to be 1 over 0, right? And so now I'm going to define, let's move over here, h double prime is equal to lambda, or I'll do it the other way. So h prime is equal to lambda h double prime, right? So now, when we introduce this over here, we get h0 plus lambda h double prime. And I want you to notice that because of the way this is defined, that these two are, this h double prime and this h prime, or excuse me, this h double prime and h0 are about the same magnitude, right? So just checking Discord for chat. Okay. So now this lambda actually means something, right? And then what we can do is I'm going to introduce one more term. So this is correct and this is correct. But I'm also going, so I'll actually write them over here. This will just be our written answer corner. H prime equals 0 h double prime, right? And we're going to do this guy here with en. So en is equal to sum all the mn's, which is equal to lambda to the negative. I'm going to introduce a new thing. Let me just check to make sure I got this guy right. Because I did yesterday. I can't remember if it's lambda m or lambda to the m or the other way around. Yeah, I did lambda to the negative m. Right. So we're going to do it lambda to the negative m. And I'm putting a bar over it. So the reason I'm doing this is because I want the magnitude of EMN to be about the same magnitude as what do you call? No, it is lambda to the m. I was right. Okay, so I'm doing this. So I want all the corrections to the energy level in this case, because the corrections are going to be smaller by the same kind of factor of lambda. You know, this is energy, this is energy, this is energy, so they're all going to be smaller by a factor of lambda. What that means is that I kind of want to scale it so the lambda actually means something, right? I don't want it to be just 1 later on. Who cares? It's just not great. So in this case, I'm going to introduce this. Now the lambdas mean something, right? So I'll do the same for psi. N is equal to sum over m n. So n lambda to the m psi n bar. So if you see a bar, it means I've scaled it so that whatever it is equal to lambda, or like whatever it is about the same magnitude, and lambda is the one that actually has all the kind of relative size info in there. Okay, so now with that, we're going to go up to this equation and we're going to expand it out. So let me also just add this here. This one's kind of important. So I hope everything makes sense to you guys right now. If not, post in the chat, let me know. You can ask questions on the Discord. I'm fine with either. So going from this We'll keep this, we'll keep this. We'll erase some of this mess because we don't need it. Right. And we moved it over here, so it's a little cleaner. So now let's just expand this out. This is going to become h0 plus lambda h double prime applied to sum lambda to the m psi bar mn is equal to sum over m e consistent lambda out front e bar m times sum. I can do a better sum than that. Well, apparently not much better, but I'll do it anyway. Sidebar and n. Okay, so if you've seen Griffiths, it's going to look like third edition. I'm talking about like between 7.6 and 7.7. So mathematically, what this will look like is, or fully expanded, times psi bar m n, well, 0n plus lambda psi bar 1n plus lambda squared psi bar 2n plus dot 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 is equal to, same thing over here, e0 n plus lambda e0 e1 n bar plus lambda e2 dot dot dot, all applied to psi 0 n bar plus lambda psi 1 n bar plus lambda squared psi 2 plus dot dot dot. Okay. So now this should be. I really hope that's visible. Once again, if it's not, tell me. So this almost looks like what Griffiths has, except I've replaced h prime with h double prime, which is scaled, by the way. So now this lambda is once again the ratio between the perturbation and what you actually, the non-perturbation part, right? As shown here, instead of psi 0n without the bars, I have it with bars over it, and those are all scaled up. So psi 0n, psi 1n, psi 2n are all about the same size. Same with e0n bar, e1n bar, e2n bar. All of those are about the same size. Okay. Finally, h0 and h double prime are about the same size too. So everything's about the same size. So in this case, the lambdas do actually physically separate everything out. So in that case, all we gotta do is collect lambdas, right? So in this case, let me get a different marker, throw some color into my life. This is a nice magenta. I hope it did turn out. Yeah, the problem with the storm is that it kind of burned out a lot of the markers, so they're not great. So yeah, we're gonna do first order. This guy doesn't have a lambda. This guy doesn't have a lambda. This guy doesn't have a lambda. For second order, let's do green. So now, or for the first order, we want lambdas to 1, right? So this guy and this guy, because this has 0 lambdas, this has 1 lambda, right? And we're also going to do this guy and this guy, because this has 0 lambdas and this has 1. Same thing over here, except now we go this guy and this guy, because 0 lambdas, 1 lambda. This guy, 1 lambda, 0 lambdas. Okay. And so now we'll do second order, and from there the pattern should be pretty consistent, or pretty easy to pick up. So once again, we want second order, so we gotta do this guy and this guy because it's got lambda squared. Do this guy, and we have to do lambda to 1. So in this case over here, we'll go. This guy gives the lambda squared here. So we'll do those two. These two go together. It's lambda, lambda, so 2 lambda. And these two go together. Okay. So you should be able to see kind of a pattern. You have like these two are the only ones that don't follow the pattern, but like these two get applied to these two, then they get applied to these two for the next order term. Then if we have 4, they get applied to these two, right? So they keep kind of moving to the right 2 by 2. On the other hand, this one, it kind of like fades in. So you got these two, right? And then you have these 4, and then these 6, right? So it expands out nicely. And if we, let's write out some terms here and actually collect them. And you can get this by foiling if you really want to, but you can just add them. So what we get is h from 0, psi bar 0n is equal to e bar 0n psi bar 0. Okay. Now, what's interesting about this specific, or actually, let's go through all of them, and then I can like expand them out over here. So yeah, let's do green 2. So in this case, we have these two. So we have lambda h. Oh, and we want it set up because if you have an infinite polynomial, the only ways I think you can, well, it'll work for like sine and cosines, but in a lot of cases, with an infinite polynomial where the coefficients aren't guaranteed to be something like sines and cosines or any kind of periodic function or something with an infinite number of zeros, to get two things to be equal, no matter what, you have to ensure that the coefficients are equal, right? And there's an extra constraint because we know that these two are in fact equal, right? So if you remember correctly, this is also because we kind of have an arbitrary constraint here in that, what about, let's do purple. So if you remember how we wrote psi n as the sum of psi mn and en as the sum of mn, e the mn. The problem with this is that I could technically like mix the orders around. I could do whatever I want with them, right? If I want to, I can switch E1n and E2n, and the sum would be exactly the same. You wouldn't be able to tell the difference, right? But because we're going to imply the constraint that the coefficients have to match the coefficients of the lambda. Yeah, they technically don't. You can like weasel your way out of it if you define these properly, but for simplicity, for ease of calculation, and because it's an arbitrary parameter, why wouldn't you make it arbitrarily easy? So we're going to pull this guy up. So this guy gets applied to psi 1 bar n plus h double prime psi 0 n. Okay, and this has to equal lambda E0 n times lambda 1 n plus E1 n psi 0 n. Yeah, I think that'll work. Okay. So now let's just do the next one while we're here. So yeah, this becomes this one is we're gonna look at the psi squared terms, and then we get h applied to this one, so this becomes 0 psi 2 plus 0 and h double prime applied to this one, so psi n. This equals psi squared n, and then we just match them all to the coefficients. So E0n has to go with psi 2n plus E1n psi 1n plus E2n psi 0. Okay. So now, I left the lambdas up there. I didn't really need to, because once again, this is a constant. You can divide both sides by it. And if it's 0, then none of this matters, and all these get 0 equals 0. And you just end up with what you started, because there is no perturbation. So I'm actually going to erase the lambdas up front for now. Okay. So now the next step is to substitute the original stuff back in. Right. If anyone can't see, please tell me. If anyone's confused on something, notify me ASAP. So once again, the whole idea of this is that in Griffiths the lambdas don't mean anything, and here I'm making them mean something. So it's like, oh yeah, well, these terms are like lambda times larger than these terms, or excuse me. I define lambda so it's smaller. This should be prime. So these are like lambda times smaller than these. All the terms here, and these are lambda squared times smaller than these, and lambda times smaller than these. So everything is smaller by a lot. So this is still the main one, and this is kind of a smaller effect, but there's some interactions between the different levels. So now that we have this, we're going to substitute everything back into everything we defined over here back in the original thing. So in this case, the first one's quite easy because all of these are lambda to the 0. So you could just do this. And lambda 0. Right. Because if we look here, I didn't explicitly write it, but EMN bar, or E to the EMN equals lambda to the EM bar. So in this case, we have 0, so it's lambda to the 0. This guy over here, same thing, except now this is also 0. Right? Same with the psi and the n, so all of these, you end up with the same equation. And this tells you that the 0th order correction is when you don't even consider the h double prime, or h prime, sorry. Moving on, we go to the next one, and this time we do actually, let me think about it. This has lambda to the -2 on it. So so I'll actually leave it up for a second. And the reason for that's not is because it'll actually get canceled out in the next step. Once again, it's a constant, so none of it matters, but like, I'd rather get canceled out with more. I'd rather get canceled out because I think this trick looks a little suspicious if you do that. So now we're going to go all the way back here, and we're going to substitute everything in. This becomes lambda prime 0. Remember, we didn't modify this. This becomes psi lambda 1n to the -1. Psi the -1 lambda n. Yeah. And this becomes plus, this time, this guy's the same, but this one carries a lambda to the -1. So lambda to the -1, h bar prime, h hat prime, I keep saying bar, lambda 0n. As above, as in here, it doesn't have anything, right? So as you can see, this lambda cancels out with these lambdas, right? And the same thing's going to happen over here. This one doesn't have the lambda to the -1 because it's to the 0, or it's the 0 term. This one does, so it has a lambda to the -1, psi 1n. Now this e has the lambda, so and then this psi 0 has no lambda because it's 0. So that's kind of the convention here, and again, all these lambdas cancel out. Now, you might find this utterly surprising, but the same exact thing happens over here. So we get lambda squared. This doesn't have a lambda. This has 2 lambda negative 2. This is lambda the negative 2. 2 sine 2n. Cancel, and it'll cancel in this term too. So this one has a lambda negative 1. H bar prime, or H hat prime, and this has a lambda negative 1. Psi 1. Right, so this cancels, all these cancel out. And this equals, all of it's going to cancel out, so I'm just going to write it as E0n psi 2n plus E1n psi 1n plus E2n psi. Okay. And if you want, you can go up do higher order terms. In fact, I'm just going to kind of give you the general rule here. Okay. So the general rule is, let's see if I can get an exact thing. So H0 hat psi n plus I should make this m plus 1. So this is psi m plus 1 h prime psi n. Yep. Equals, and so now we're going to do this sum from, well, I is not a good one, iterator. So let's do k equals 0 to m of e k n psi n minus k n. Excuse me, these are m's. M minus k, and this is, I'm all over the place. So yeah, this upper one is an m, this lower one is an n. That's the standard. So this is like all these equations. I'm just gonna box it and put it there. I think that should be good. Yeah. So, and you can think of this may look a little scary, but it's basically just this and this have to add up to this. When you take, so like here, they both add up to 0. This one's kind of a weird case, it doesn't count for this one, so like everything else. But here, you have psi 0, psi 1, and then this, well, this side is just there. So in this case, m is 0. And this guy over here, well, you can see that 0 plus 1, 0 plus 1, down here, 0 plus 2, 1 plus 1, and 2 plus 0. All of these are pretty much the same. They all add up to the same number, and that's all this represents. So, like, 5th order perturbation or something like that would be something like, second order is when they all end up at 2. Once they have to add up 5. So this would be like h0 psi 6n plus h prime psi. So this is like 5th order perturbation theory equals e0n psi 5. Wait, hold on. This is second order, this has psi 2, so this needs to, so we need to go to this needs to start at 0, and it needs to go all the way up to m plus 1. So plus 1, right? So in this case, m is 1, and it needs to go from 0 to 2. Okay, so then this becomes m plus 1 minus k. Okay, so I guess we're doing 6th order perturbation theory, but it's this plus 1n side the 5n plus 2n side the 4n plus e to the 3n psi 3n plus e to the n 4 psi 2n plus e 5n psi 1n plus e 6n psi 0. Right, so I just, if you look at this, this would have psi to the 6. This would have no psi, this would be psi to the 1. Or, excuse me, this would have a lambda to the 6 attached to it. This would have no lambda. This would have a lambda to the 5th. This would have 1 lambda, so that, you know. So that's all it is. So you can kind of expand it out pretty naturally. And from there, you can do all kinds of calculus, or excuse me, you can do all kinds of little math stuff there, but it's good. So what I'm gonna do is, I guess I'll write this up. We don't need this anymore since we've already done everything. So I'm gonna move up here and rewrite this equation there. Right. So it's basically h0 psi m plus 1 n plus h prime psi n equals sum m plus from k equals 0 to n plus 1 e to the k 0 n times psi m plus 1 minus k n. Right, so that's what all the terms in the perturbation theory come up to. And so if you want an nth order perturbation, you're going to have to solve this equation. So moving on, we're going to I'm going to erase this as nice as it is, but and then I can just rewrite it. So the first thing we're going to work with is this one. So, or excuse me, this one's the corrected one without all the lambdas. Probably should have rewritten that, but we're going to work with this one, so it's h prime 0, and I can also do it from here. Psi 1 n plus h psi 0 n equals, and then we go whatever this is, they have to all add up to, so e0 n psi 0 psi 1n plus e1n psi 0n. Okay, so this is what we end up with here. So now we're going to use a few tricks to really rewrite this, because with our psi 0 n's, those are an orthonormal set, meaning that, or complete orthonormal set system, a complete orthonormal set, it doesn't matter. And what that means is that basically you can represent any equation as within the interval, like pretty much any equation or any function as a weighted sum of our psi's, right? And so that's what you get with the Schrodinger equation. So you get this guy here. And so our first, so this is a classic trick. We're gonna rewrite these in terms of bras and kets for reasons that'll become clear. Second, we're about to take an inner product, so let me just erase this. 1n psi 0, and then this becomes equals, and then little slim, but I think we'll live. So now, what we're going to do is we're going to take the inner product of this equation, because we can represent it as vectors. Yeah, we're going to take the inner product of this guy with psi 0 n. And the reason we want to do that is because we know what psi 0 n is, because we've already solved the Schrodinger equation with the unperturbed state. So we know what this is. So we can at least calculate something conceptually. But there's also another bonus. What will end up happening is we'll end up canceling out certain terms that'll make our life easier. So let's do that. We get psi 1n 0 psi 1n plus psi 1n prime psi 0n equals psi 1n plus, excuse me, n 0 1n plus psi, oh, excuse me, this was I said psi 0n and then wrote psi 1n, and then I wrote a 0, though it's just like a 1. Man, you'd think drawing a circle would be easy. Sorry. Doing perturbation theory? Wait a minute. No, I gotta try harder on my circles. Psi 0 n E1n psi n. Okay. So now, what we're going to do is pretty straightforward. You might look at this and say, oh, can we cancel out these guys? Can we cancel out these guys because they have different indices? Well, no, because remember, it only applies with these guys, with m and n, and these being 0. So our original set is this. So we could cancel this out. If we had psi 0n and psi 1n, we could cancel them out. But in this case, we can't, because we don't know this, and what we'll find is that we're actually going to want to express this in terms of this. So now I'm going to first see if I can do some simplifications here. Yeah, so I think I'll do the simplification first. So this is just a constant. We can pull it out, and then we're left with psi 0n, inner product with psi 0n. Definition, that's 1. So we're left with E1n. So I can just write that here. And some videos so you guys can go back and watch it. Man, I'm a little picky about my handwriting today. Well, probably because I'm recording for you. Okay, so that's one thing we can do. Right. The next thing we can do is we can actually take this en out. We can't do anything with the inner product yet, but we'll take this E0n out. Front. Okay, that was the next step. Now, that's fine. I want to point out that they probably just like tried to take the inner product with something they knew, which is why they picked psi 0n. I don't know if it'll work with other things, but it works well with this, so we're gonna keep with it. So now the other thing is we gotta notice that this guy is Hermitian, this operator. So what that means is we should be able to switch it. So this applies to here, and we could do that, or we could like take its, well, it equals its adjoint, so we can conceptually get some space down here. I'll write it in, I guess, let's do magenta again. Magenta's a cool color. So psi 0n 0. And this property, the ability to move from applying to this guy to applying to this guy, is because it's Hermitian. That means that it equals its complex conjugate. In less mathy terms, it means that if you apply it to something, it has real outcomes. So because energy can only ever be real, it has to have it has to be Hermitian, and if it's Hermitian, we can do this with it. Right. So moving on. But this guy applied to this guy. Well, we know what this guy is, right? That's what we started with. I erased it a while ago, but remember our original equation, the unperturbed equation, was I gotta use black. We used to have a good black marker, but then it just died on me. But anyway. Right? So we know what this is because this is what we started with. Is it getting darker? Let me turn on a light. I think something's moving. Okay, that looks a little bit better. It might be a little harder to read like that number, but it's been on the board for a while, so I think we're good there. But yeah, so you take this guy applied to here, and well, because we already solved the Schrodinger equation for this guy, we know what this operator does to this guy, and just turns this into a constant. So that means that we can write this as E naught n psi 0 n psi 1 n, right? But this is a constant, so we can pull it out front, which equals E 0 n psi 0 n psi 1 n. And wouldn't you know it, look what happened, look what shows up on the other side of the equation, this guy, right? So what that means is we can cancel this guy from both sides. It's the same guy. And that leaves us with the equation that Griffiths gives here, and so we're left with another 0 n one n. Okay. And this should kind of make sense. Yeah, the first order correction of the energy is the expectation value of the perturbation in the unperturbed case. So basically, you apply the perturbation to the original wave function, and that gets you your next estimate for the energy level. And then what you'll end up doing is you'll kind of end up kind of laddering up. You'll get your wave functions in one order of perturbation theory. Then when you go up a level to get your next equations, right? Or you'll get the energy from one level, right? Then you'll go up a level to get your wave functions, and then you'll go up a level to get your energy for the next order, and then you're going to go up a level to get your equation from the next order, and you'll kind of end up laddering like that. All right. So now that we got that idea, once we get the first order correction of the energy, then we can start doing some stuff. So let's go back to this equation, right? And we know what this is. So we're going to plug that in a second. But for now, I'm going to kind of leave the bracket notation off. It kind of doesn't matter. It's like, it's kind of like x hat for the x position, right? It's like 5x hat versus 5I plus 2k, right? And these hats mean unit vectors in a direction. They don't mean operators, but that's why I'm not using them, and probably why they don't use them in bracket notation, but, well, part of the reason. It may not be the original reason, but that's like where we've started. So let's go back here. H0 psi 1n plus H1 psi 0n equals E0n psi 1n plus E1n. Okay. So real quick, I just want to go through all the knowns just so that we have them. We know what this is, right? We know what this is because we solved for it earlier. We know what this is. These are given, right? So the only thing that we have left to solve for is psi 1n. So knowing that, that makes it a different color. Yeah, let's mix it a different color. I probably should mix it. I'll just divide it, but yeah, we haven't used purple yet. So now we want to get all the psi 1s on one side and all the psi 0s on the other side. So H0 n 2 7 1 in. Hope you didn't hear that one. Just burped. Right? Equals negative h prime psi 0 n minus 1 n psi 0 n. So I subtracted this from this side and this from this. I subtracted this from both sides, subtracted this from both sides, and I flipped it over so like they were kind of symmetric and like this. And let me just make it a little better because if I'm going for symmetry, I might as well go full way. So yes, okay. Right, so now here's the thing. We know what this is, right? Because we know what the first energy level, it's this up here. And we know what this is over here because this is given to us. We know what this is, so this just becomes a differential equation. But we can actually make it a little bit nicer on ourselves. So remember when we said that these were an orthonormal set of basis functions? Or I said an orthonormal set, a complete orthonormal set. It's an orthonormal, so like you can imagine, I can write any function as a weighted sum of these guys. And we're going to do just that. Yeah, I think it's got a little bit of a benefit because we're dealing with wave functions and quantum mechanics, that all of them normalize to 1, so any problems that you could have, because it's kind of like for a Fourier transform, you're doing something similar, or Fourier series, they have to be periodic functions, but they have to be periodic functions that are nice in a way, otherwise it just won't work. L squared integrable or something. Yeah. So now what I'm going to do is I'm going to re-express this in terms of the original basis functions. And then we're going to try to figure out some coefficients. So what that means is I'm going to say psi in general mn is equal to some coefficients cmn psi 0. So I'm basically going to say whatever coefficients I get, I'm going to... Oh yeah, there's actually there's a third index here. Okay. Wait, hold on. Psi 1n. Okay, so yeah, I'll just make these k's. Right. Yeah. For some reason he has an n down here. Oh yeah, there is a third index, so... Oh. We put he as, and I'll just rewrite this. Let's be a little less ambitious and rewrite this just for psi 1. Okay. So now that means everything is written in terms of psi 0k, right? And he said k does not equal. Well, he's using m's, but I don't use m's in other places, but I think I'll stick with the k's. Alright, so psi 1n and k does not equal n. Right. Sorry, just checking certain things, make sure everything's up and running. Okay, so... And the reason we don't have the k equals n term, right, is because we already kind of included it up here. So let me just write it out. So let's say we have, let's say we do psi 0, 0, right? And then there are some other terms which we're going to ignore. and we're going to give this a C. C. I'll put both zeros up top, so it's just different. It's like this zero corresponds to this one corresponds to this one. It's not too important. But anyway, so yeah, we do this guy, and then we're going to do psi 1 plus psi 1. Now I haven't normalized it because normalizing would be multiplying everything in here by a constant, so the constant kind of has it in there, or maybe you could make it normalized. I don't really care. But if we expand this out, what we'll end up getting is, if we don't include the k equals n, we'll get c0, 0 plus some stuff plus this own c0 k, or no, t0 0 psi. Okay, and you can see that these, I could just add these together. So I could just C0, 0 plus C0 times psi 0, 0, right? I could add these together and absorb it in this constant. So we explicitly don't include it. And it'll become a little bit more clear later on down the line, because we'll actually just straight up remove, we'll straight up end up having to remove it, and it ends up dividing by 0. So we're just not including it because it gets absorbed into the main one from higher up. Right. So yeah. Put this into this. And we take an inner product. Yeah, that's pretty standard. So I'll do that in one step. And then they do psi 0 L. This L has nothing to do with angular momentum or anything like that. It's not like one of the quantum numbers. It's just an index psi 0, 0 applied to sum. This sum's going to disappear in a second, so who cares? K not equal to n. C K psi K. As you can see, this will only exist for L equals K because orthonormal. So going back here, we have negative H prime E minus E1 n psi 0. Right. Oh, and then we take the inner product of this. Did he change it up on me? No. Okay. Okay. So we'll do psi 0 L. I'll move the negative sign in. It's not that big a deal. Prime psi 0 n. Okay. Right, and so here's the trick. Oh yeah, so and then we'll apply this to this first. So we're gonna need to do some expansion. It's not gonna be great, but we can do it. Yeah. So we need to expand this guy out. Yeah, I'm getting okay. So sorry, I'm just trying to be very deliberate about this. This guy and this guy will cancel out. Okay, let's do this. okay, so you apply this guy to this guy, right? And you end up getting E0k, right? So what this would get us is, but this gets us the L. Yeah. Oh, okay. I think for the moment we're just assuming they don't interlap for some reason, but it's going to, or we don't. They don't overlap, but it's going to end up overlapping in a second. Sorry. So anyway, psi 0L 0 applies to this, so this gets us CK N. This gets multiplied by N. Oh, and then get subtracted. So yeah, so that for a second. Okay, so psi 0 N. This gets applied here. They both get applied here, so we can bring them inside. So sum k not equal to n, c k n, h prime 0 minus e. I keep saying prime, I mean bar, and then bar when I mean prime. It's a mess. Okay, so we got this guy in here, and now I'm going to do one thing real quick. This applied to this equals E0k. Okay, right, that's the whole point. That's what we have over here. So we get this guy set up. And furthermore, these are all constants with respect to this, so we can bring it out front. Some k not equal to n. And yeah, if at this point we're going to end up dividing by this term, and we don't want it to be 0. So anyway, we bring this guy out front, we get c k n E0k minus E0 n times psi 0L psi 0k. Okay, so we worked a little on that side. Let's jump back to this side. This just becomes a constant, so this becomes E1n psi 0L psi 0n. This guy applied here becomes, what do we say this becomes? E1n? No, I can't. Oh, yeah, no, we don't know what it is yet. So this becomes minus psi 0L psi 0 and there we go, right? And then this applied to this is going to end up turning into E1. That's good. Right, so let's say we're going to say that L equals N, and that will give us some kind of room to work with. So assuming L equals N, that means that this is 1, so this becomes E1. And I'm going to replace this with 0. N, or I say assuming, but we can just plug in any value of L we want. Let's just let L equal N. This becomes 1 because it's psi 0n, psi 0n. This becomes psi 0n, my h prime psi 0n, right? So this guy becomes this guy, and we end up getting E. So we get E1n. Okay. And in case you're wondering, we're solving for this constant here. So yeah, and then just messing with this. Oh, if L equals N. So at some point they changed it to amps, like, which is kind of annoying. Oh, I was doing K, so I'm using K instead of N. Right. So if L equals N, this becomes this. This goes to 0, right? And then we want to look at real quick. Let me just do a quick change in notation. Yeah, they did. Yeah, they did it with m's and but they had an n up there. But now somehow I got n's in my denominator. I think it's this. Yeah, so they have m's here, and this will make my life a little bit easier. M, 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 M. I think that's an. No wait, that's an M. Right, and if they're using m's. Oh no, these would all be k's. Okay. So that's what I'm missing. These would be k's. And another k. I just rename my variables, now I'm gonna go weird. K. And this becomes other way around. K minus. Yeah, because they're applying this here, and this is just 0. Yeah, there's some. Okay, so this side does have ends. And this. Oh, okay. Okay. So they had this, and this side doesn't have any ends. Except for one here. This is an n. But this side, everything over here is an n. So yeah, I think let's just get. These are n's, so we're back where it started, which is cool. And this is not. This shouldn't have been a k. Okay, I think we're gonna go 0. So let me see. Man, I switched out 1k for an m, and the whole thing just goes to this. Okay, k. K's. Oh. Yes, they did L equals 0. And so this. L equals n. Oh, because the sum is not over n. So if L equals n, then k never equals n, so this whole term goes to 0. On the other hand, this. Man, there's something messing with me today. Yeah, what the hell? Oh, if L doesn't equal n. So if L equals n, everything just goes to like 0. This term goes to 0, so it gets 0 equals 0. We don't get anything. But if we assume L doesn't equal n, then let me go back a step. I think that's what's giving me up. Okay, so yeah, now I'm starting to see it. Okay, so L doesn't equal n, this term goes to 0. L doesn't equal n, this term is this term. Right? And L doesn't equal n means that we get one term out of here, specifically L. So we end up the inner product of this with these, and these are basis vectors. This will only work if these two, if L equals K or K equals L. So that means that C L N E L minus E N. Run that farther over. Equals negative sine 0 L H prime sine 0 N. Okay. So what that means is our C L is equal to negative 0 L prime sine 0 N over E0 L minus E0 N. And so this is where specifically we have to assume L doesn't equal N for some stuff up here because it gets 0 equals 0. Or we get like one term equals 0. Something like that, but here it really has to be different. And this is why we need like degenerate perturbation theory, because this actually works. So as you can see, this is there. So now that we know the coefficients, we can plug this back into here and get something pretty cool. We'll get right up here, psi 1n is equal to sum k not equal to n of this guy. Let's add a negative out front, negative sum. Or let's not add the negative, let's just switch the order of subtraction in the denominator. So E0n minus E0L psi 0L H hat prime psi 0 N. Right. So normally they would overlap. Or normally that these two would be orthonormal if you applied the Hamiltonian to them, because it just gives you an eigenvalue, but this could change the effect of psi 0 N. So yeah, there we go. If there's any point where E0n and EL0L are equal, then we're screwed. Unless, if your perturbation doesn't depend on it depends only on your radius, or, no, I'm sorry, I'm thinking of hydrogen atom. If it's degenerate, but like in other dimensions, or you pick a perturbation that doesn't actually work with it, or how do I put it? I'll stand back for a second just so you guys can look. I'm gonna erase it. But yeah, let me try to get second-order perturbation theory. Basically, if there's degenerate perturbation theory, you have to you can't just use psi 0 n. You can't use these as your raw basis functions. You have to kind of turn them a little bit, so you end up doing linear combination of them. We'll get to that in a second. But moving on, let's try second order. The second order, we take this equation, right, and I'm gonna erase all this. Second order, I feel like I can make that blue. I think that's what I did earlier. Second order, we just take this guy, and once again we do psi 0 n, the classic. Or we take the inner product with psi 0 n to get the energies. Right, in this case m equals 2 because we're doing second, or m equals 1 because we want, this is the order, m plus 1 is the order. So we'll do h prime 0. Yeah, we just straight up did it like this, so we'll do that. Plus, and I think after this I'm gonna try one problem or two. I don't want to go too long on it. if anyone has a request, I'd be down to do that. Psi 1n equals, okay. So let's start simple. E0n means that this has to be E psi 2, and so psi 2n plus 1n psi 1n psi 1n, or excuse me, psi 0n psi 1n plus E2n psi 0n psi 2 psi 0. Yeah. Right, so we just took the inner product with both sides. We're going to do the same trick we did last time because we can switch these around and this one up canceling out with a nasty term, specifically this one, right? So it's the same trick we did for first order perturbation theory, but let's do it here. So those two cancel. And furthermore, this guy goes to 1 because it's just this rule, our classic friend. This guy goes to 1. And so we can solve for E2n, right, by taking this guy and taking this guy, subtracting over both sides. So we get 2n equals prime sine 1n. So that's this guy minus E1. Oh. Minus E1n sine n sine 1. And let's just separate that out so there's no confusion here. Okay, so once again, we should know what this is automatically. Yeah, actually. In fact, we know exactly what this one is, I think. Yeah, we know exactly what. Okay, so remember when we did psi 1n equals this, but k doesn't equal n? So in that case, there's no single n. So we basically run into this case where the only one that would survive is k equals n, but k does not equal n. So in fact, this whole term goes to 0 too. So we're just left with this guy, and it's pretty nice. And once again, we know what this guy is, we can expand it out. So this gets us psi 0n. The only term that survives, yeah, I'm pretty sure that the only term that will survive is the psi 0n. Yeah, okay, so I actually need to expand this out. So I'll do this. Sum k not equal to n, c n k, psi 0k. Right. So then this applied to here is on, or this applied to this. I think that gets us. Well, no, we won't know ahead of time. Okay, yeah. So they don't get rid of the sum because once again, if you apply this to this, you don't know if it is equal. So like we applied this to this, the L and the N are different. We don't know if they're equal, but we can make this substitution, or we can bring everything in here. So let's do that. equal sum k not equal to n. See n. Okay, so at this point, it's basically just like taking what you know already, plugging it back in the original one, using stuff like orthonormality. There's nothing crazy going on here. But something to look out for: side 0 n, h prime, side 0 k. And like k. Okay. So now we got this c in k, right? But we know what that is. I didn't write it down. Well, it's this term, but I need to write size 0. That's so that's missing a term there. Whoops. Yeah, we need size 0 k. Man, really not choosing M was screwing me over. But okay, so there we go. So yeah, in this case, it's not too clear, but you look at this guy, you look at this guy, this is clearly your C and K. So this ends up being equal to K not equal to N. And so I just want to make sure I'm really getting this right so you don't, waste your time. Well, I say waste your time, but I've already some of that. Anyway, size 0 n 1 size 0 k, which I'm putting the absolute bars in there because it's going to get squared. But if you notice, we already did this. This shows up here, and it shows up here, right? So this just gets squared. And then we take the E0n minus E0l, but this time we're summing over k, so E0. In fact, let's actually sum over k instead of l. Can't believe I wrote that down so incorrectly. Anyway, M to k screwed me over for the rest of this. Anyway, so we do E0k, right? Yeah, this is our E2n. I did write our E1n, but let me. It's not too hard to remember. It's actually one of the easiest ones because it's E1n equals size 0 n. Apply the perturbation size 0 n. So that's En1. E2n equals sum k not equal to n. There's some variation there. Sorry. I thought for a second I could plug an E1 in there, but N and K are different. So prime size 0k squared. All that divided by E0n minus E0k. Okay. So now we got that guy there. We got our energy levels. We have side 1. Yeah, there's you could do the second order equation. I'm not going to. They don't recommend doing it. It's just that's as far as you normally get where it's still useful. So I'm gonna stop there. Let me just check the Discord, see if there are any questions. No, I think I picked a bad time to stream, but I'll live with my what do you call it? I'll live with it. Anyway, so those are the equations, and you could derive them again. It's just nice to have it generalized, but it's not too crazy difficult to do it without the generalization. Sort of like how there's okay. So this is jumping to a totally different kind of topic, but there's an explicit equation. So This is from electrostatics, you don't need to know this. Well, if you're a physicist, you do need to know this, but okay, so like this is Poisson's equation. It's a restatement of. Let me get it exactly right. It's Maxwell's equation del dot E. So the divergence of E equals this, but you assume that's a gradient of this, and you do some stuff. It's nice. It works out. Anyway, if you, man, hope I can remember my train of thought. Well, there's an explicit. There are multiple explicit equations for it. If you want in terms of basis function stuff, I think it's like. Well, in Cartesian coordinates, in Cartesian coordinates, it's something like some e to the negative alpha x plus e to x, and there are coefficients in front of here, so like c111, c22, or like that stuff times. Like there's an explicit formula for it in terms of basis functions, but I don't memorize it. Normally I solve it. This one though, I understand the process. I understand how you do it. It turns out to be just a bunch of simple algebra, so I don't know how much I'd memorize the formula. I definitely memorize this one because it's not too hard. Just plug the perturbation into there, see what you get. Right? Next order level, well, that one's a little bit more difficult. You're probably taking an open book test, so you can look it up. Like conceptually, that's what it is. It just turns into a bunch of algebra. You plug these things in, you re-express the terms of basis functions. Nothing freaky there. So yeah, there's. Yeah, and normally you only calculate the first few terms because it just gets too small. Let's we'll apply perturbation theory to most general two levels. Yeah. So I think this is good for like covering non-degenerate perturbation theory. I wanna give you guys like a real example, something you can like look at and see this, because there's a certain thing in there that's I guess how it relates to matrices. So like some of you guys get confused on matrix elements and like what does it mean, but I need to write this one down. This one's a good one. Well, I already wrote it down over there. But yeah, normally you just kind of live life with it. So in terms of you live with the energy levels and you don't go much further, because once again, like for something like normally you get things that are ordered in the order of like a fine structure constant, so each one's like 1/100th the size of the previous one. But then you add like two of those. Once you get to that, the wave function's only 1/100th difference from, or 1/10,000th at least difference between the two. So it's kind of like, how much effort am I really willing to put into this for no correction of the wave function? But you can, with the energy levels, it's a little bit nicer because, even though it's still small, it's something there, but like the difference in probability in a region for a wave function, I don't think it's going to matter too much. So yeah, this is problem 7.4 from Griffiths. And this is the most general two-level system. So what we have is h prime 0 plus, or h prime 0 is equal to E0 A 0 0 0 E. Okay. Let's do our month 6. So I want to see how fast we can do this. And we're going to set that h prime is equal to EAA, EAB, VBA, VB. Okay. Definitely shouldn't have done this before. Yeah, and it needs to be Hermitian, so I'm actually going to write this as V AB complex conjugate, right? So it equals its complex conjugate transpose, and VA and VBB are real. So, but yeah, okay. So what exactly does this mean? Well, what it means is like normally when you do a matrix, you normally do something like this. So if I wanted, so let's say we have 1, 1, 2, right? And we had a vector 1, 2, 3. Well, mathematically, what this would do is scale in the, and let's say this is x, y, z, right? So this would scale it in twice the z direction. So we end up with 1, 2, 6. Right? I'm not going to do the full multiplication. You can do it on your own. So we scale in the z direction, right? But here's the thing. I could, if I wanted to, I could also write this vector as x hat plus 2 y hat plus 3 z hat, right? And so now I can define each of these to be like, in this case, x hat would be 1, 0, 0. Y hat would be equal to 0, 1, 0. And z hat for completeness sake, but you know the pattern, 0, 0, 1. Right, so I could express it like that. Okay. So now, normally you apply the Hamiltonian to a wave function, right? And each wave function has different states, so like these guys, right? In fact, you may have heard the term eigenvalue eigenfunction thrown around. It's because, in this case, they're all the in this case, what would the eigenvectors be? This is degenerate, so it's not good, but let's do 2, 3. In this case, it scales twice this and that in the y direction. So, quick. The eigenvectors are 1, 2, and 3, so this becomes negative 1, 0, 1. Times this. Yeah, so these are also the eigenvectors, I think. Yeah, so these are the eigenvectors, alright? So if you get a diagonal matrix, the eigenvectors are just these guys, right? Okay, so now what I'm gonna do, and this is something that shows up a lot, is I'm going to, instead of writing the states out like this, so I have like, let's say my wave function is equal to, and I'm ignoring perturbation theory right now, like C0 psi 0 plus C1 psi 1 plus C2 psi 2 plus dot dot dot, right? Now what I'm going to do is I'm going to say, okay, well, psi 0 is going to be 1 all zeros, right? Psi 1 is going to be a 0 and then all ones, z and so on and so forth, right? So let me make it more explicit. I'm going to erase this for a second, right? But you can see that these x hat goes here, the y hat can go here, the z hat can go here, and then there aren't an infinite number of letters, but you can imagine the same pattern continuing. Okay. So yeah, you have this guy, right? And then let's apply the Hamiltonian to it, right? You apply this, and then we're just going to apply it. Well, this equals C0, apply to psi 0, right? Plus the Hamiltonian in there. Plus C1, Hamiltonian, psi 1, plus C2, Hamiltonian, psi 2, plus dot dot dot. Right? So it just keeps going on forever. But we know that we've set it up so that the Hamiltonian applied to this gets us the nth energy thing, right? So let's go. I have too much red on the board right now. Red's my favorite color, but I have too much of it. So I'm actually going to use pink, nice little compromise. And it's back. I crossed over to blue earlier, so now it's kind of like this kind of cool color, but anyway, so we set it up so that C0 we apply this to here, and we just get E0 psi 0 plus C2 E naught psi 1 plus C3, or excuse me, E1 E2 psi 2 plus dot dot dot, right? So now consider what happens if we just focus on this one. Say C2 and onwards. Say C1 and onwards are all just 0, right? So in this case, we would just have C0. 0, right? So now conceptually, let's say we want to represent this as a matrix. Actually, let's just keep it. Let's say we want to represent this as a matrix, right? So in this case, what am I going to put? Yeah, we're going to keep it simple for now. So I'm just going to tell you this. Everything that's not on the diagonal is just zeros. Right? And this matrix is also infinite, so it's... And the returns all in here. Right? And the reason I can say that everything is, except the diagonal is 0, because if I apply... because this doesn't change, right? So if I apply Hamiltonian to this, it's still size 0, it's just scaled up, right? So in this case, what you end up with the Hamiltonian is E0, E1, E2, dot, 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 and then like E, I guess, infinity if you have an infinite number of things, or you can just say E n and let it go to infinity, or let it go to infinity if you need to, or you could say, well, it's just a finite number of terms. So, so like in this case, E would be 2, so E0, E1. And then you see E0A, E0B. So they're using zeros, so note that it's not perturbed, but A, E0, B, they're similar. So I could have just as easily written A, B, C, D instead of 0, 1, 2, and so on. Okay, so now, but let's consider a little bit of a weird case. What happens if, say I got these nice size zeros, right? But there's something weird. If I apply the Hamiltonian to psi, right, I don't get just something nice and clean like this. What I end up getting is, say, C0, 0 psi 0 plus E1 psi 1, right? Plus, and then it has to be complex conjugate transpose, so that means it has to be symmetric. Plus C1 E0 psi 0 plus E1 psi 1. Right? And then let's say that C2 and everything else is regular. Right? So now, well, I'll keep the consistent notation. So everything else is pretty regular, right? So in this case, the off-diagonal terms of the matrix can't be 0, and we can figure out exactly what they are. So I'm just gonna E2 n, and then we're gonna do 0. Well, actually, there's no space here. 0. Just like this is all zeros, and then this. These guys are all zeros, right? But here it's going to be something a little different. So let's just say I multiply by E1, right? And I'm going to say that. So we're going to keep the convention that 1. So this would be if it was entirely pointing in the size 0 direction. Ah, cool, I'm getting spammed, it looks like. In the chat, at least I'm getting chat. Maybe they think they're good. They think I get spammed. Anyway, so yeah, so I got this guy. So now, if we apply it here, what we end up getting is row times column, and this will get us our first row. So what we end up getting is E0, right? So this guy, E1 because of this guy, right? And then all zeros for the rest of it if we multiply this out. So that means that row times column means that this guy has to give us E0, right? But then if we do this again, so take the next one, we do row times column, so forth, right? What this means is this has to give us E1. Right, that's the only way to get this column out. Okay, so we know what those are, and then yeah, it's kind of weird the way I wrote it. In fact, let me. Yeah, I'll just leave it for now. But anyway, now let's do the other one. So let's assume that we just have this. So this would just be just this term, right? So we nuked everything. There's no E. It's just like this, right? Normalized. So in this case, oh, this is still E0, and this is still E1, right? Okay, so now we multiply this out. 0. To get this guy, this gets us to the second row. So we need to do so wait. I think what ends up I think the easiest way. Oh, hold on. So let me go back to step 1, 0. Okay, so E0 is this. That gets us that. So then this would have to be 0, but that's not accurate because we also need to. So like, yes, this would work, but no. If we multiply by E1, then we have to get the same thing, right? So let's switch it up a bit. I'm just gonna make it simpler on myself. So I'm just gonna say you operate on E0, you get this, right? And if you operate on this, you switch these two. And I'm just making this up as I go on. There's no like fundamental basis for it. So that means that 0, 1. So this has to get us E1, and this has to get us E. Okay. So now we kind of end up in a weird kind of like double state here where these both have size 0 and size 1 in them. And the important thing is like, and this E1 is not necessarily the first energy level. What it means is that our matrix doesn't have nice thing. We haven't, size 0 is not a basis function, size 1 is not a basis function, right? A basis function, you apply Hamiltonian to it, you get one number. You don't change the vectors at all. You don't get anything scaled, right? So, but we got different vectors. The direction changed, so it's not an eigenvector. It's not an eigenfunction. Right, so we get something like this. So now what we need to do is we need to find out what we could make these values, how we can change these up so that we can get an eigenfunction, so that we can get an eigenvalue. And so what and then in this case, this is where you have to find the eigenvalues and eigenvectors of this matrix. I'm just gonna do that real quick. The squared minus E1 squared has to equal 0, so it's pretty clear that that lambda equals plus or minus E1. Lambda equals E0 plus or minus E1. Right, so now if I do that and then I plug that back in, this becomes negative E1, negative E1. Yeah, so then our two kind of sub-matrices. I'm just doing a little bit of math, but it's like if I plug in negative E1, right, and I subtract them, I get E1, E1, one. If you have just segments of the diagonal where everything else is zeros in the area, then you only need all this stuff will get you whatever is on the diagonal is going to be the eigenvalue. In this case, eigenvalues are energy. It could be other things as long as you don't change the state. This guy here, this 2x2 is going to have its own eigenvalue. If there was 3-level degeneracy, this 3x3 would have its own eigenvalue, have its own set of 3 eigenvalues. A little bit of linear algebra. So, one. Okay, so that's one of them. So so we apply E1 to this guy. Oh no, it needs to be E0 minus E1. So I'd recommend looking at some linear algebra a little bit for it. But E0 minus E1 here. So what we have is E1A plus E1B has to equal. Oh no, this shouldn't be up here. Yeah, up here. You probably won't have to do this. Well, you will not have to calculate an eigenvalue, so I would look into that. Plus E0 and minus B. And I keep putting the B's down here because I keep doing it up here. Okay, so we'll just solve for these. So we get 2E1B because I moved it over here plus or equals E0 minus A. So then we have yeah, we'll do B. B equals 1/2 E0 over E1 minus 1A. So your eigenvector. This is kind of a weird way. I'm messing around too much, but you would want to normalize this. So go ahead, normalize it. I'm not going to because fight me. 0, 1 minus 1. Okay, so what that means is basically instead of psi 0 and psi 1, one of your vectors should be, you should be doing something like psi 0, so you should represent it as like C, I'm going to put tilde over it. So C bar, let's do tildes. C tilde 0, psi 0 equals, or psi tilde 0 equals psi 0 plus 1/2 E0 over E1 minus 1 psi 1. So you can like re-express it in terms of this. I picked some bad numbers. I apologize for that. Yeah, I'm probably have to go in like 5 minutes. So anyway, what ends up happening, I didn't get to degenerate perturbation theory, but you can kind of imagine this matrix element thing here. This is what it is. It just means this. In fact, you can explicitly say that if you want to represent in matrix form, that. Otherwise, this was kind of. But yeah. So there's a process called diagonalization in which you rewrite everything in terms of different basis vectors that are much nicer. So then it's just a multiplication across. It's just simple. So in this case, you don't get diagonalization. You have to manually diagonalize. That's what happens in second order and degenerate perturbation theory. You end up with two things with the same eigenvalue, and normally that means you have to diagonalize it. Or maybe I'm just focusing on one specific thing. Anyway, let's apply this. I'll give you the rule. So if Q is an operator, and what we're going to say is that Q psi. Here's the rule that you. Let's start writing left to right. psi I. Now let's do m and n. M q psi n equals lowercase q. So what this means is basically, in this case, what it means is if I were to write out, like, let's say we were just write out a second order, so like this only has two possible states, right? So in this case, you could do psi. Well, yeah, let's do psi 0, and then we count 0, 1, 0, 1. Just be psi 0, h psi 0. This would be psi row versus column, so 0h psi 1, psi 1, h psi 0, psi 1, psi 1. Now, normally, if you pick an eigenfunction, if you pick eigenvectors or eigenfunctions for these guys, then h bar applied to here will get you a constant, but then you end up with psi 0, psi 1. So if in an orthogonal system where psi 0 and psi 1 are orthogonal, you can do this. H psi 1 equals, and we'll define orthogonality in a second, psi 0, E1, psi 1. You can pull this E out, so you end up with E1, psi 0, 1, right? And then normally this equals 0, right? Because you've done your work. If you do differential equations properly, if you solve the equations, if you do all the math and stuff, you end up getting, by default, this property, and that's what this represents. On the other hand, if you get something weird, right? So for a moment, say we don't, say our h bar, oh, and by the way, the weirdness thing is you need this to be true. So h bar applied to this, it scales this, but it does not change the direction, all right? So it doesn't add anything. On the other hand, say we do this, 0, and we do with some q operator, psi 1, right? Say for some reason that expands out to this. So q actually expands out to two things. So let's say E0 psi 0 plus E1 psi. Oh, let's make it q. Let's make it lowercase q. I don't want any association between this and energy levels because they don't normally do this. Can't happen. So then, now you look at this and go, okay, well, this guy still goes to 0, right? Because it's psi 0, inner product of this, that's a constant get pull up. But this guy doesn't, so you end up getting q0, right? So now, you pull this guy out. Oh, I need a shirt cover. Anyway, it doesn't matter. But you get this guy q0 out, right? So then you'd have a q0 here. You'd have a q0 here. So then down here, you'd also have a q0 because this h applied here, you could apply it here first. Complex conjugate, so you get q0 conjugate, and then here you get q something. So yeah, and then oh, here's the thing I was missing. I think q0 and q1 have to be equal. Because I could also have applied this to. I could have also done this, and then this would get me. Yeah, so this would end up applying if they end up equal. It doesn't matter, but anyway, we've expanded the matrix out. We've got some stuff going. It's kind of the idea. So I'm bringing this up because one of the people I was talking to mentioned it specifically. He was kind of confused on what was going on with spin. It's kind of a step back, but basically there's x plus, so you have like c plus, let's do up, plus c down, and minus, right? And then yeah, so this turns into be a matrix with c up, or no, this turns into a vector, c up, c down, right? So in this case, this is for spin. So you have this kind of axis. It's a probability, so it has to be constrained to one, so circle. But you could be here, you could be here, you could be here, you could be here, and this is this spin up, spin down direction, right? And so this might look weird because okay, this is up, yeah, because that looks up, but this is down. Wait, this isn't down. This is down. Spin down is over here. Once again, you're not talking about specific position in space. You're talking about probability of measuring something. So if you're in this state, right, you take its x position, you square it, you get the probability it's going to be spin down. You take its y position, you square it, you get the probability it's going to be spin up. And you add them together, you get 1. So that was kind of something a little tacked on the end there. But yeah, that just the general idea of how the matrices work and stuff like that's pretty important to know. In general, I would say this is shorthand for a matrix. Right. Actually, I shouldn't. That's not necessarily correct. I think this is probably better. QMN, and then Q equals Q00, Q01, Q02, dot dot dot. 10, Q1, Q12, dot 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 dot. That's how the operators work. And with vectors, once again, same thing. So we'll call this like C1, C2, C3, dot dot dot. This equals C1. Normally it's psi1. It doesn't have to be psi to be anything, but C2, psi2, C3, psi3 plus dot 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 all the way to infinity. And then if you want your raw vectors, so if you want C1, first off we're going to conjugate it. Well, I'll leave it as is, but like you conjugate when you flip it, so. Wait, no, this is a vector, so I can conjugate. So if I do complex conjugate transpose, so this would be. That was a cough, I think I'm just. Or that was a cough, I think I'm just inhaling a lot of fumes from the markers. And I ate some food. Okay. So anyway, this gives you C1 conjugate psi1 plus C2 conjugate psi2 plus 2 conjugate plus C3 conjugate psi3 okay. It's kind of like indirectly covered, but once again, this doesn't have to be size. For example, in terms of spin, you could have written this like C up, C down equals C up. I'll do the plus and then plus C down minus, so stuff like that. So you just need to get in your head that you can express these as linear operators, which means you can express them as matrices, which means you can do this, and that's kind of the idea. So once again, normally if you have eigenfunctions, this always gets you the same thing back, and because these wave functions are the functions are orthogonal, you end up getting 0 and everything. So you end up with only diagonals. So that's what's up here. Psi1 and psi2 are, or psi A and psi B are accurate for the system. So yeah, I can do the first order energy level corrections. Yeah, actually, that's not going to be too bad. So E1n is equal to, so we'll do psi 0n. We'll call this, so this is 1, 0, complex conjugate, but it's whatever. A, E star, A. I'm going a little fast. There's a pretty good chance I'm going to make a mistake here. VAB. but this should be correct. Yeah, so then you can see that it's going to be equal to VAA for the next one, and then E. So this is E1A, this is E1B equals 0, 1, VAA, V star AB, VAB, VBB, 0, 1 equals VBB. So there's like a free 5 points on your test when that happens. Let me see if I can go back, check it out. I think I'm probably going to do degenerate perturbation theory later. I left the lambdas out because who cares? Real, blah, blah, blah. Find the exact energies for this two-level system. Expand your result from area to second order. So then if you want second order, we do this. Oh, and then E1, EA is this, EB is this. Right. And then second order, I know there's some overlap here. There it is. There it is. Okay. So second order, let's do those real quick. So E2N, so E2A equals sum K does not equal N. So there's only one other possible K, so this is K equals B. So E0A minus E0B. And then this guy here is psi 0A H prime psi 0B because they can't equal, right? And this is simply E0A minus E0B all over. I'm going to put that in there, and then you can see that I'm just going to keep this up here. But psi 0A is this guy, psi 0B is this guy, so we're going to call him VAB, VBB, but then VAB, so this becomes VAB, VAB, and as you can guess, the same thing is going to happen for the other guy, except now it's going to be EB0 minus E2A, because once again you put the one that you're dealing with first, this EN. And then instead of this, you end up flipping this guy because now you're doing psi 0 in first. So it's magnitude squared. And then this guy is just going to be VAA, V star AB. And so that's VBA. Then you want the second one, so that is going to be star squared. So this is the this is the first correction. Here. I change it. Oh, I changed them both, so I'm just going to go back to this, keep it consistent. And there's the second order energy level changes. And I am right about over. And then if you want the eigenfunction, you just plug them in here. So psi 1A equals, there's only one term in there. Or it doesn't matter. Yeah, order won't matter. So we end up with E0A minus E0B. And then that guy is just going to be AB. K first. And we can do VB. Conjugate VAB. It won't matter because, once again, wave functions are scaled by all kinds of stuff. But psi 0B. Right, and then psi 1 is going to equal. Same thing up there, except now it's not conjugated, but it doesn't really matter. Going a little fast, there's once again, chance I might mess up. This part doesn't matter because it's conjugated for whether or not. So E0B minus E0A psi 1A, right? So those are all the like energy corrections, stuff like that. And you just kind of plug them in, get the idea. Nothing too difficult there. All right, so I'm gonna end the stream here. I hope you guys enjoyed watching. Have a good one.